All right, let's talk about multi-leader replication strategy today. Recall that last time we talked about single leader. The bottleneck for single leader is the fact that all writes have to go through a single node before it gets replicated to the followers. Uh, so that creates a bottleneck on the database, right? Where all the writes has to go through that one node. In multi-leader replication strategy, we're defining our database cluster through several data centers. So if you look at this drawing here, pardon the sketch, my very rough sketch. So if you have two data centers, right, DC1 in SEA, Seattle, and DC2 in LA, Los Angeles, right, we have one user. This database contains, let's say, a leader and two followers. And this database contains a leader and two followers as well. Right, replication, remember from single leader, replicates and replicate. So our user, let's draw him a little closer. Let's say he is in Seattle, local, he's a local Seattle person, and he's making a call to a database, and he writes name. Let's see, I should redraw this. Name is equal to John. Right. So he makes an update to the database, and the database replicates to the follower. But now it also needs to replicate to the other leader, which is all the way in Los Angeles. Right. So there's a new replication channel. Right, and this replication channel is typically a service. So it could be a side service, right? So some kind of replication that talks to each other. So what we could do here is the replication channel reads the, let's say, the bin log or some kind of database log behind the scene, and so he reads the log and then it talks to the other replication. And as the replication service here detects changes, it sends the signal to the leader in this data center to make the update, right? So if we look at this very rough sketch again, right? So this guy, our client, sends an update request to data center 1 in Seattle. The leader makes the update, and the replication service sees that the bin log has been updated and sends the update all the way over through the network to the other replication channel, and then it updates the other replica, right? So on the contrary, we can do the same thing here. Like if there's a second user that's making a database call, let's say he's updating name is equal to Jack, right? Same thing. So it's going to get the bin log change and send that change over, right? Send that change over to the other replication service, and it performs the replication. So that's the kind of high level of how multi-leader replication work, and specifically, we are talking about uh, multi data center, right? Okay. So what are some kind of key things to know? Well, the real key thing to know about multi-leader replication is conflict resolution. You can see that we're adding additional complexity to our system. So we'll run into conflicts. Right. Previously, in a single leader replication schema, we didn't talk about conflicts because all the writes go to the same leader node. But now, because there are two leader nodes, writes can happen concurrently. So conflict resolution becomes a very important subject for our multi-leader and even leaderless schema. So the first way that we resolve conflict is by having no conflict at all. So number one, we can try to completely avoid conflict. Right. But as you know, in software, everything has a trade-off. So what's the trade-off? Well, how do we accomplish completely avoiding conflict? The way we do it is by doing something called home routing. So home routing simply means all record. Let me put it this way. We can, what is that? We can try to completely avoid conflict using home routing. So home routing just says certain keys must go to let's say XDC, right? So in this, let's say we have key range. So in the database, key range, just for simplicity, key range is A to Z, right? The whole alphabet, right? A to Z, and maybe, yeah, let's just say A to Z, right? And we have two data centers. We can say that in data center one, all A to H must go to data center one. All keys A to H must go to data center one, and all key I to Z must go to data center two, right? So in this case, we have name. Name is the key is name, so we need to send the record to the second database, right? Hopefully that makes sense. And by doing that, we can completely avoid any conflict because all of the writes has to come here in a synchronized manner because the keys are specified to go into that database, right? So if somebody else, let's say if a person 3 wants to write name is equal to Jenny, right? Then it also has to go to the second database because here we mapped from I to Z. Again, we add complexity by doing this. We add what kind of complexity? Then we need to have a metadata service. So there needs to be a metadata service that maps the key to the actual to the database. Alternatively, we could use a hash value to specify where it must go. So yeah, add just a little bit more complexity. We can either add a metadata service, or we can say okay, hash some kind of let's say we hashed by the size of, or this is modular. Let's say we mod by the size of the cluster. Okay, so that's the first way we try to completely avoid. The second way is what we call last write wins. Pretty straightforward. Last write wins. This is the more straightforward one, where we attach a timestamp to our key to our request to our request, and whichever request came in first gets the whichever request came in last gets the update. So last request is the one that stays, one that wins. Right, fairly straightforward. This one, last write wins. Okay. So there are a couple of key things to watch out for lost right wins is that we're very prone to data loss. Right. Very prone to data loss because the first person is going to write John thinking that it succeeded, and the second person is going to write Jack thinking that it succeeded, and the third person writes Jenny thinking that it succeeded, right? But then when they get the value back, they're all going to, see Jenny because Jenny is the last one that updated. So it's prone to data loss. Now the third way, we can merge the value together. If we merge the value together, right, we concatenate, let's say what we get is name is equal to John, Jack, or we should do this alphabetically. So let's say we use red, Jack underscore Jenny underscore John. This way it shows that there's a conflict. There's a conflict in this record, and we can then resolve the record manually. Manual resolve, okay? And we can resolve it using two ways. So we can do on write or on read. This basically just says we resolve the conflict during write. So as we write, we can get the value back to see that there's a conflict here, and then we resolve it, right? So whoever is the person calling is the person making the database change. He could say, okay, I want Jack, or I want John, or Jenny, right? And on read is the same thing. When conflict is detected, all the writes are stored, but it's resolved on the read request. Okay. There's also automatic. So automatic conflict resolution. Automatic conflict resolution typically revolves around CRDT, so conflict resolution data type. Conflict resolution. Just make sure I got CRDT right. Conflict-free replication data type. I'm sorry about that. Conflict-free resolution data type. And this we will discuss closer in more detail in a later series, later video. And this is, going back, the most important thing to know about multi-leader replication is these couple ways of resolving the conflict. All right, thank you.